इतना ही बोलना है. So this talk, I have not prepared proper slides for this. So this talk will be unusual because the topic is also unusual. The way this talk I have arranged is, there will be one slide with mathematical jargon. The next slide will be blank, where I will give you the physical perspective and you can ask any question and ask as many questions as you have. So we will basically look at the mathematics with a physical lens. Then the next slide will again be mathematics. So the way this will go is mathematics, physics, and so on. So I have just prepared 7 slides, and after each slide there will be a blank slide where we will discuss physics of the mathematical jargon. So if you have any questions, you can ask. Anyway, should we start?
Yeah.
Okay. So the topic is exceptional Lie algebras, and we will understand each of these words today. What do you mean by why it is called exceptional, and what do you mean by Lie algebras? And to begin with, what are algebras? So each of these has a mathematically rigorous definition. But what we will do is we will limit the mathematical rigor and keep it to the level which is enough for a physicist. And then we will ask what are its implications in physics and why is it interesting for us. Part of my work is based on this, and currently I am also pursuing this for my future project. So I love to talk about this topic. So let's start. So first slide will be very mathematical, but don't be scared of that slide. We will go to the next blank slide where we will discuss as many examples and as many physical perspectives that you want, and you are allowed to ask as many questions as you want. So don't hesitate to ask questions. So let's start. So the first part is, since the topic is exceptional Lie algebras, are the slides moving?
Yes. Yes, they are moving.
Okay. So as you can see, this is not very well written, but we will try to get the main idea out of this. So what are algebras first? So we all know what is a vector space. So on top of the structure of vector space, you have additional rule, which is a product rule. So for example, if you take real numbers with the rule of addition is a vector space. Now for the real numbers to be an algebra, you have to also give a product rule. So you can take that rule to be a usual multiplication. And with that, this rule should satisfy some properties such as closure. So if you take two elements from that set and you compose it through this product, you should get another element from the set itself. And also, there is a property called distributivity, which is not necessary for us. So I have not written it here, but that is how the algebra is defined. So R is also an algebra. Apart from being a vector space, it's an algebra. In fact, it's a field. We will not go into the details of field and all those things. But so the important point here is a vector space with a product rule. That is an algebra. So apart from this, you can think of the space of matrices, square matrices. So square matrices, you can add matrices, right? So it's a vector space. The space of matrices is a vector space where in the vector space, the rule of addition is the usual matrix addition. And on top of that, you can also define matrix multiplication, and that makes it an algebra. Now, what is a Lie algebra? So for the purposes of this talk, you should think of Lie algebra as a set of matrices. Okay. And the product rule here is actually a commutator. So it's a set of matrices where you have a nice commutation rule that is defined. So the rule 1 and rule 2, which you can look here, XA XB commutator is FABC XC. So what does this tell you? If I take two elements from the set, that these are like matrices. So take two matrices, find what is the commutator of the two matrices. You will find that it is a linear combination of the elements of the set. So the right hand side is just saying that you compose two elements through this rule. The rule is the commutator. You will get a linear combination of the elements. So this is like closure property itself. But the rule here is commutator rather than just a normal product. Okay, and the second property is called Jacobi identity, which we will not go into the details of that. So So for the purposes of this talk, because we are going to focus only on finite dimensional Lie algebras, I will make this statement clear. What do you mean by finite dimensional Lie algebras? So for this talk, you should think of this XA as matrices. So this capital X is a Lie algebra. So it means it's a set of matrices and it's finite dimension, which means it has finitely many elements. So this small d here, A equal to 1 to D, this means that is the order of the set, and it is also called the dimension of the algebra. So whenever I say dimension of the algebra, I mean how many elements are there in the set. Okay. So I hope this is the mathematical setting. Now we can ask what does all of this mean. So let's understand this better. Okay. So does anybody have any question on this definition?
So can we say that polymatrices form a Lie algebra?
Which matrix?
Polymatrices?
Yes, they do form a Lie algebra, and in fact, that Lie algebra is SU2. So we will see.
Yeah.
Yes, we will see that also. So very good question right now can be, what is the difference between Lie group and Lie algebra? Why am I not talking about Lie group? I am only talking about Lie algebra because for a physicist, this is what matters the most, because most of the times we are concerned with infinitesimal rotations. So I will roughly give you the physical picture. The physical picture is the following. So Lie group. So I hope you can see what I'm scribbling.
Yeah. It's visible.
So Lie group is, for the purpose of this talk, mathematicians will not like this definition. This is a very naive definition, but for us it works. Lie group is exponential of Lie algebra. So all elements in the Lie algebra, they represent infinitesimal rotations. Very small rotation matrices. Okay. And this side, this Lie group side, this represents finite rotation matrices. So rotation by a finite amount. So what is a very good example for this? Take this example, usual SO2 rotation in two-dimensional plane, cos theta sin theta minus sin theta cos theta. This is a finite rotation. So this is actually belonging to the Lie group SO2, which I write in capital letters. So what is the definition of SO2? It means all 2 by 2 matrices which satisfies this property. R transpose R is identity 2 cross 2 with determinant of R equal to plus 1. Correct? Cos square theta plus sin square theta is 1. So this is an element of a Lie group. So as you can see, the element of Lie group is parameterized by a angle theta. So there are infinitely many elements in Lie group. Lie algebra has a finite number of elements. Okay, because these are also called generators. So the elements of the Lie algebra are also called as generators, and there are finitely many. Why? We will see this. So take the infinitesimal limit of this. That is, take theta tends to 0 limit of this matrix. So let's call this matrix M. And when I take theta tends to 0, let's call it delta M. Okay, or let's call it some new matrix N. So what do you get? When theta goes to 0, you will get 1. Sin theta you can expand, for small thetas, it will just be theta, right? This will be minus theta and this will be 1 again. Correct? Now I will write on the top because I don't have space. So you can write this N as identity plus theta times 0, 1, minus 1, 0. So this is like identity. This is identity 2 by 2 plus this theta is a small parameter. You can think of this as epsilon. And this matrix, okay, this matrix I will call it as the generator of the SO2. So this is actually the Lie algebra of SO2. This 0, 1, minus 1, 0. This single matrix generates the entire Lie group of SO2. Okay, all these things will be clear right now. Why there is only one generator? Okay, so that has to do partly with the number of independent elements that you can write. So see, R transpose R is identity, right? So you can write R as exponential of some matrix. Now, if R transpose R is identity, that means R transpose is R inverse. Then you can show that this matrix actually, which belongs to the Lie algebra, M. So we were using the, so let's call this a new matrix N prime. This N prime must be antisymmetric matrix. Okay. This you can show. We will do this in detail. So a 2 by 2 antisymmetric matrix just has 1 degree of freedom, right? If you fix that one off diagonal element, the entire matrix is fixed completely. So only one generator is there. So we'll make all these things precise, but roughly the lesson here is Lie groups are basically finite rotations, and they are represented as exponential of some parameter times the generator. The generator means infinitesimal rotations, and these infinitesimal rotations belong to the Lie algebra, which is the focus of this talk. Okay, so I hope this is clear. Are there any questions? Okay, if there are no questions, I'll move ahead. So as I said in the previous slide, Lie algebras, we will be only focusing on finite dimensional Lie algebras here. Okay, and the dimension of the Lie algebra is nothing but the number of elements in the set. Okay, and that is equal to D. Because here we took this A from 1 to D. This D we will find for different cases. What is this D? What are the number of generators for different kinds of Lie algebras? Okay. And as I said earlier, for the purposes of this talk, it is useful to think of the elements of the Lie algebra as square matrices with certain properties. We will specify what these certain properties are. In certain cases, these matrices will be antisymmetric. In certain cases, these will be traceless Hermitian matrices. In certain cases, they will be symmetric matrices. So depending on the definition, these matrices will have additional properties. Okay. And so this is all we need. So what did these two mathematicians do, Elie Cartan and Wilhelm Killing? They classified all finite dimensional Lie algebras. Now, how is a Lie algebra specified? The Lie algebra is specified through its structure constant. This FABC, which appears here on the right hand side, this is the most important thing of a Lie algebra. Okay, this specifies the Lie algebra. So apart from the matrices, the dimension of the matrices, this FABC is something which actually fixes the algebra. So, so if you want to consider finite dimensional algebra, that means a set which has finite elements. What all sort of Lie algebras you can write? That's the question that this gentleman asked. And what did they find out? They found out that all finite dimensional Lie algebras can be classified into 4 families. Okay, and most of you have heard of all these algebras. First is SUN plus 1, simple unitary Lie algebra, which acts on a complex space of n plus 1 dimension. So Cn plus 1. Then the Bn and Dn, this SO2n plus 1 and SO2n, these are just orthogonal Lie algebras. So this means infinitesimal rotation in real space of even and odd dimension. So there is a distinction between a Lie algebra of even dimension and Lie algebra associated to rotations in even dimension and in odd dimension. And the third one, that is the Cn, that is a symplectic algebra. And so all of you have studied classical mechanics. So the canonical transformations actually belong to this Lie algebra, this SP2, infinitesimal canonical transformation. So all of these appear somewhere in physics. SU2, for example, the Pauli matrices, as was mentioned earlier, these appear in quantum mechanics, right? The SO groups, for example, appear as symmetries of the three. For example, for our world, we have 3-dimensional symmetry, rotational symmetry, right? So SO3 is the group that we look for, and then we study what are called representations of this. So that's a different topic. But all of these appear somewhere, and these are what we call symmetries. naturally appear as symmetries of the physical system that we are studying, right? So the most important word here is symmetries. That is what physicists like, and this is what greatly simplifies the problem. Okay. So are there any doubts? Next slide is blank, so I'll wait for any questions that you have. Okay. So so here one question will arise. What is this n here that I'm so all this a n, b n, c n, and d n, all of them have a subscript n. What does this subscript mean? So this is what is called as the rank of a Lie algebra, and we'll understand some of the technical details associated with this shortly. So let's move forward. So since there is not much mathematical jargon here, I will not write anything here, and we will move to the next slide. So obviously the question is, why bother about these algebras in physics? So one very standard example that is always given is the standard model of particle physics, which, as we all know, describes the strong, weak, and electromagnetic interaction. And the Lie group on which it is based is SU3 times SU2 times U1. So it's important to understand what are these Lie groups, what are the mathematical properties of these Lie groups, to better understand how these forces play around in nature and how the matter content basically talks to each other through these forces. And what is important here is not just the Lie group, but what mathematicians call as the representation of a Lie group. So once you have a Lie algebra, what you can do is you can basically find some kind of higher dimensional matrices which mimic the same algebra as the Lie algebra. Okay, then that matrices, that set of matrices is called a representation of the Lie algebra. So literally it is a representation of the Lie algebra because it just mimics the set of these matrices mimics the algebra associated with these matrices mimics the Lie algebra. Okay, so that is why it's called representation. And as we all know, the different particles that have been observed till date, they are we think of these particles as representations of the symmetry group of the spacetime. The symmetry group of the spacetime is the Lorentz group. So, for example, we have scalar particles which are called spin zero particles. They don't transform under the Lorentz group. You have photons which are spin one particles. You have the weak force particles, that is W plus minus and Z, and the gluons. These are all spin one particles. So all the force carrier particles in the standard model are bosons, and all the entire matter content that we have in the standard model is basically composed of fermions. And fermions, as you know, are half integers, spin half representations basically. So so this is about Lie algebras in physics, and we look for symmetries because it simplifies the problem to a large extent, right? For example, if you have two charges in space, if you have a single charge in space, you know that the field that is produced by the potential that is produced by this charge is spherically symmetric. So you can just write it in terms of the radial coordinate r, and solve all your problems. Like solve the then suppose you place another charge somewhere and you want to find what is the dynamics of that charge under the force of this electron. Then you will obviously employ the spherical polar coordinates, and you would not try to solve the problem in Cartesian coordinates, because the spherical polar coordinates takes care of the symmetry of the theory. So it simplifies the problem. You can easily see that that angular momentum is conserved in this in these coordinates, it's very apparent. It's not that in the Cartesian coordinates you will not be able to solve. You will be able to solve, but it will be complicated. So it's always better to understand the symmetries and then solve the problem. That simplifies the problem a lot in physics. Okay. So, since we have discussed physics, let's go to mathematics. So, given a Lie algebra, so as I said, representation of a Lie algebra in very loose sense, it means that you want another set of matrices which are in general of higher dimension. Okay. And they have the same algebra as the original Lie algebra. Okay. And if you want to find this representation of Lie algebra, you must understand the structure of the Lie algebra. So this is very similar to quantum mechanics. So in quantum mechanics, when you are given Hamiltonian, you always solve for the eigenstate, energy eigenstate using the Schrodinger equation. But if you notice, you also find all those operators which commute with the Hamiltonian. Why? Because mutually commuting operators have the same eigenstates. So all mutually commuting operators can be written as diagonal matrices. So the same thing happens here also. Since there is a commutator involved here, a Lie algebra has a subalgebra. All Lie algebras, all of these finite dimensional Lie algebras, these have a subalgebra, which is called as the Cartan subalgebra. So what is this Cartan subalgebra? It is just a set of maximal mutually commuting elements. Okay. So if H, which is a subset of X, is the Cartan subalgebra, then HAHB is 0, where AB goes from 1 to n. And this n is called the rank of the Lie algebra. So basically, the number of elements in the Cartan subalgebra is the rank of the Lie algebra. And why is this significant? Because now you can clearly see what the Lie algebra is. The Lie algebra is composed of diagonal matrices which commute amongst each other, and these form a subalgebra of the Lie algebra, which is the Cartan subalgebra, and other matrices which are non-diagonal. All of them are non-diagonal. Okay. And I will give a very good example in the next slide of this. Okay. So, the structure of the Lie algebra is clear, I hope. X, that is the Lie algebra, it splits into, so I have split it into two parts. One is the Cartan subalgebra and the other, which I call as the coset, and it is written as X over H, where H is the Cartan subalgebra. So it splits into diagonal and non-diagonal matrices. Diagonal matrices all commute amongst each other by definition, correct? And these will have a common eigenstate. Okay. And these non-diagonal matrices, if you have studied quantum mechanics, you know that there are these raising lowering operators in quantum mechanics. These are very similar to that. So let's look at what with an example. Let's look at what are the Cartan subalgebra and what are the coset of SU2. Okay. So let's take this example, SU2. Are there any questions right now? I hope I am connected. Hello.
You are connected.
Yeah.
Okay. So I will give you an example. So take SU2. So when I write this as capital, this usually means Lie group. Mathematicians are very careful about all of these things. And when I write in this way, this usually means the Lie algebra. So as I told you, Lie group has infinite number of elements and it is exponential of the Lie algebra. And we are concerned with the Lie algebra here. So SU2 has a Lie algebra and it is a very simple set, and you already know what are those elements. Sigma 1, sigma 2, sigma 3. Or let's call it sigma x. Just a minute. Sigma x, sigma y, sigma z. What are the properties of these matrices? These are Pauli matrices. We know the explicit form of these matrices. Sigma x is 0, 1, 1, 0. Sigma y is 0, minus I, 0. Sigma z is 1, 0, 0, 1, minus 1. Now, can you identify the Cartan subalgebra out of this? Very easy. sigma z is the only diagonal matrix. So that is the Cartan subalgebra. So H is just sigma z. And as you can see, sigma x and sigma y are non-diagonal matrices. So this sigma x, so x over h is basically sigma x, sigma y. Correct. And now you can arrange sigma x and sigma y in a particular linear combination such that it acts like raising and lowering operator. So take sigma x plus I times sigma y and sigma x minus I times sigma y. So that is like j plus and j minus. And this sigma z is like j3. So this together will become j plus minus. And then you can find representations of this algebra. So very simple example. These are the generators of SU2. Why they are generators of SU2? What is the definition of SU2? We will look at that later. But just consider right now this set of Pauli matrices. Okay. And so I hope this construction is clear. This is the Cartan subalgebra here. This is just one element here. So there is nothing to do. And apart from that, there are just two other elements. Okay. One more point. Yeah. Now observe interesting properties of this matrices. Sigma x, sigma y, sigma z, all of them are Hermitian matrices. So sigma x dagger, or let's say sigma I dagger is sigma I. Correct? All of them are Hermitian. All of them are traceless.
Hello, Nipun.
Hello.
Yeah, I have a question that you said that to form those lowering and raising and lowering operators, you need to take the linear combination as sigma x plus I times sigma y plus minus I times sigma y like that. So what decides those coefficients of those linear combinations? So how we decide, how we fix that I and those factors? So I can take any arbitrary linear combination like alpha sigma x plus beta sigma y. So how I fix
Yes,
those?
you can. Yes, you can do that. Yes, you can do that. But the important point is you have a 2 by 2 matrix, right? Here you have a 2 by 2 matrix. Now, so the way SU2 Lie algebra is defined is it is actually complete set of traceless Hermitian matrices. Okay, correct.
True.
So the only diagonal matrix that you can construct which is traceless is this only.
Yes.
All others will be just independent. So there is only a single matrix that you can construct which is
Sigma Z.
traceless and Hermitian.
Traceless and diagonal. Yeah.
And any other matrix can be just obtained by multiplication.
And another will be identity if there is nothing else.
Identity is not traceless.
Yeah. Identity is not traceless.
So it does not belong to this set. Now, apart from this, now you want to ask what are the number of diagonal elements that I can write. Okay, so instead of this sigma x and sigma y, somebody could have directly written some sigma prime x as 0, 1, 1, 0. Okay, and sigma prime y as 0, 1, 0, 0. Because these two matrices, they span the non-diagonal space, right? Any non-diagonal matrix can be written as a linear combination of the sigma prime x and sigma prime y. Correct?
Exactly.
So to begin with, you could have started with this also. And this is the simplest choice, in fact.
Yeah.
And this is nothing but j plus and j minus. If you check by computing this is nothing but j plus and j minus actually.
Okay.
And so these kind of matrices which have only a single non-zero element in the non-diagonal, these are very nice properties. Okay. These are very special matrices because when you take the commutator of such a matrix with a Cartan element, okay, you get back the you get back the Cartan element.
Cartan element itself by some apart from some constant. Yeah.
Yeah, exactly. So this is a very special property of this. Sorry, not the Cartan element. I think you get J plus back.
No, if you take J plus minus with J3, you will get I think something 2H cross J3 itself, I think. Or J plus minus. J plus minus.
No, plus minus J plus minus, right? Or maybe you're right.
I think it's J3. Yeah.
Because J plus with J minus is J3 actually.
True.
So So J3 with J plus should be
J3 is J plus is J plus minus plus J, something like that. Yeah.
Correct, correct. So what? So my point is here, these non-diagonal matrices with exactly one non-zero element in the
Hmm.
non-diagonal. These have very special properties, and always you will find any Lie algebra.
Hmm.
These kind of matrices will always be the raising lowering matrices.
Okay.
Now, to begin with, you can just start with this algebra. Instead
Yeah.
of this algebra, I can just start with this algebra. There is no problem. There is a unitary transformation which will take me from this sigma x, sigma y, sigma z to sigma prime x, sigma prime y, sigma z. This is equivalent,
Okay.
right?
Okay. Okay.
This is just a change of basis
Okay.
kind of transformation.
True. Yeah.
So, uh, so there is no problem to begin. It's just the definition that you have to start with, and then so you have to just identify those matrices which will
So,
act like. Huh.
so instead of yeah,
You can ask.
instead of taking this sigma x, sigma y, I can start from the beginning with J plus, J minus, and J3 and define the algebra in terms of those.
Exactly.
And that
Exactly.
defines my Lie algebra itself.
Yes. Yes. Exactly.
Okay.
Yeah. By the way, one small note here. Usually, mathematicians will not like the way this J plus and J minus is defined. I mean, it is defined with some I and all this. They are very careful with even multiplication with complex elements.
Complex.
It depends on what kind of field, on which field you are considering the Lie algebra. Is it over real or complex? And
But that I factor we can always absorb in the other matrix.
we can. I mean, for us, matrices should be Hermitian because all observables for us are Hermitian matrices.
We need
and they have
Hermitian.
real,
That's why we pull a I factor out of that.
exactly, and they have real eigenvalues. So, we are not so much, looking at this factor of i's and all those things. But
True.
ultimately, so this is the point here. So, any Lie algebra, finite dimensional Lie algebra, you just separate it into diagonal matrices and non-diagonal matrices, and that too, those non-diagonal matrices have the property that each non-diagonal matrix has exactly one non-zero element. All other elements are zero.
Okay. Okay.
And these are the special kind of non-diagonal matrices which will act like raising lowering operators. Okay. So this is a very important point. Okay. So I hope this point is clear. So,
Yeah. Thanks.
so I'll proceed ahead. So as I said earlier, so let me go back to the slide where I mentioned about the work of. So as you see, this A n, B n, C n, D n. These are four families of Lie algebras, and these are infinite. Infinite in the sense n is an integer, and you can take any large integer. So these are infinite families of Lie algebras. And apart from these Lie algebras, there are exactly five Lie algebras which do not fit into these categories, and that's why they are called exceptional Lie algebras, and they have very good properties, and also they have found their place in physics, both in high energy and in condensed matter. And no wonder that a Soviet physicist was also behind this discovery of this E8 symmetry in this Ising model. Their work is always very nice and illuminating. So yes, so let's understand each of these series a little bit. So as I've told you, the sigma matrices have the property that they are Hermitian and they are traceless. So that is the way the SU2 Lie algebra is defined. Okay, and why is it defined in this way? Very easy answer for this is take this Lie group. The way this Lie group is defined, this SU2 Lie group, it is just the matrices U satisfying U dagger U equal to identity 2 by 2, right? And also determinant of U equal to plus 1. This is the property of SU2 Lie group. I'm talking about Lie group. Now what did I say? I told you that you can write a Lie group as exponential of a Lie algebra. So that means I can write it as exponential of theta I sigma I. Correct. Let's put an I here. And what will be U dagger? It will be exponential of minus I theta I sigma I dagger exponential of I theta I. So this I is summed over. So let's not confuse. Let's write it as theta dot sigma. Okay. And here you have a dagger. Now sigma, so because sigma dagger is sigma, you see that you will get identity from here. And because you want this u to be determinant 1, correct? Now u is exponential of this automatically implies that the trace of sigma should be 0, because if u is equal to exponent of I theta dot sigma, then determinant of u is nothing but proportional to trace of sigma or exponential of trace of sigma, right? So if sigma is traceless, then determinant of u is 1. So that are the properties that you require for the Lie group. And that is why the Lie algebra is defined like this. It is the set of traceless Hermitian matrices 2 by 2 in the case of SU2. And the same thing you can do for higher dimension, that is SUn plus 1. Correct? It is a complete set of Hermitian traceless matrices. Okay. Now what is the dimension of SUn plus 1? So now to count the dimension of SUn plus 1, you want to find what is the dimension of this vector space, right? What are the number of independent Hermitian traceless matrices that I can write of order n plus 1 times n plus 1. Okay. Now the answer is n plus 1 square minus 1. This you can try. It's very easy. Then we can ask the next question: what is the rank of this algebra? That is, what are the number of elements in the Cartan subalgebra? So since it's a n plus 1 times n plus 1 matrix, right? So how many elements will it have in the diagonal? N plus 1 element. And since it's Hermitian, diagonal is real. So there are n plus 1 real elements. But it's also traceless. That means the n plus 1th element will be related to the other n elements because of the trace condition. So only n elements are independent. So I can write only n diagonal matrices which are Hermitian traceless. That will be the rank of the algebra. Okay. I hope this point is clear. If you have doubts, you can ask here, because this is a very important point.
Can you show it once by like?
So what do you want? Do you want this answers, both answers, or
I mean the last point, why it is n plus 1 minus 1.
correct. So let's first look at SU2. See, SU2, you had 2 by 2 matrix, right? So it's 1 plus 1. In n plus 1 language, it is 1 plus 1.
Yes.
And since it's Hermitian, only real entries are allowed in the diagonal, correct? So how many such independent diagonal matrices can I write? See, I can start with A, 0, 0, B to begin with, but I know A plus B should be 0. What does this imply? B should be minus A.
Right.
Which means I can write any matrix as A times 1, 0, 0, minus 1. And this is the only independent matrix. All other matrices are linearly dependent on this matrix.
Right.
So there is only one element in the so there is only one diagonal matrix which is Hermitian traceless, right? That this happens for a 2 by 2, means SU2. So for SUn plus 1, because of this trace condition,
1 is subtracted.
1 is subtracted. So it is n plus 1 minus 1. So you can only write n. So the Cartan subalgebra, the order of the Cartan subalgebra is n. So there are n mutually commuting matrices. All of them can be simultaneously diagonalized. Okay.
Thank you.
Any other question? Okay, if there are no more questions, I'll proceed ahead. So since this slide is clear now, let's move ahead. So this Bn and Dn series, this is the orthogonal Lie algebras in even and odd dimension. That is rotations in even and odd dimension. So this I will slightly leave as a exercise because it is I will give you the definition: a complete set of antisymmetric real matrices. That's the definition. You have to find all independent antisymmetric matrices of dimension 2n plus 1 cross 2n plus 1 and 2n cross 2n. That is even and odd cases. and find what is the dimension of this Lie algebra. So dimension of this Lie algebra means how many generators do you have? How many elements are there in the Lie algebra? And rank of Lie algebra means how many diagonal matrices can you write, which are also antisymmetric. That is like so diagonal. So all antisymmetric. So there is no diagonal matrix which is antisymmetric, right? So this question I think is tricky here to answer. When I say diagonal matrix, but you can think about it. I mean, so here I will physically argue what do you mean by rank. So when you say commuting, so in quantum mechanics, when we say two operators commute, what does this mean? If I measure an operator A and then measure an operator B, value of operator B on a system, that measurement will be the same as if I flip the order of the measurements, right? So A and B are not affected. The system is not affected. Sorry, that's not the right way to put. But A and B don't affect each other. The measurements of A and B don't affect each other. That's the meaning of commutator of A and B being zero, right? So imagine if you have a four-dimensional space, real space. Okay, so x, y, z, and there is another fourth coordinate. If you do something in x, y plane, if you do a rotation x, y plane, will it affect the rotation in zw plane? It won't, because this zw plane is orthogonal to xy plane completely. These are completely different planes. So there is no connection between rotation here and rotation there. So for four dimension, the rank of the Lie algebra is 2, or the number of elements in the Cartan subalgebra are 2. So you can do this for any even dimension. For 6, you will have 1, 2, 3, 4, and 5, 6. These are like independent planes where you can do rotations. So you can find the rank is greatest integer of d by 2. Okay, so you can do all of this. You can find what is the dimension of this Lie algebra and all those things. By the way, if two matrices have to commute, it doesn't necessarily mean that they have to be diagonal. As is this example, SO2n plus 1 and SO2n. But I have argued here physically what is happening. I hope this analogy is clear. Let me draw a picture probably. So you have one plane here, and there is another plane which is orthogonal to this plane. So let's call this x1, x2, x3, x4. So there will be a generator. For each plane, there will be one generator. Because earlier we saw SO2 has one generator. Plane means SO2. Okay. So each plane has one generator. Because in a plane, there is only one axis around which I can rotate. Right. So there is only one generator per plane. So if I do a rotation in x1, x2 plane, it will not affect a rotation in x3, x4 plane. So these two operations will commute. So generator from this and generator from this will always commute. And this will be the maximally commuting set. Any cross terms, any cross rotations you do, that will always affect this rotation and this rotation. Okay. So the maximal set of commuting elements that you can find for SO4. So because I am considering four-dimensional space here, that is 2. So that is the rank of the Lie algebra, or the dimension of the Cartan subalgebra. Okay. So I hope this is clear. And now another thing is clear, why this is greatest integer of d by 2. As you can see here, it is greatest integer of d by 2. If I add another axis here, still the number of independent planes are just 2. It has not increased. So still you will only be able to find 2 elements which commute, not 3. So, but the number of elements in the coset are now different because there are more rotations that you can do. So that's why structure of the even and odd dimensions is different. The structure of the is there a question?
Can you explain the last point once again?
This rotation?
Yeah. When you add some other axis, why is not increased?
See, I have already exhausted the number of independent planes. when I am finding the cartons of algebra, I am finding the number of independent planes. What do I mean by that? Planes which are orthogonal to themselves. So a rotation in one plane doesn't affect the rotation in another plane. Okay. So now if I have a fifth axis, so you have x1, x2, x3, x4, x5. Okay. You can do a rotation here. It won't affect a rotation here. Correct.
Yes.
But now you have another axis, but that doesn't add any other plane, right? It's just a single
Do you
axis.
mean
Huh.
that at every point there will be only two rotations which won't affect each other?
At every point, yes.
Even
means
though
all
if you
points.
have, even if you're adding one more axis, x5, you will still have only two pairs of planes whose rotation along whom will
Correct.
not affect.
Correct.
Okay, so it is redundant to have x5.
That's why this greatest integer function is here.
Okay.
So both for even, so if you take SOD where D is any even or odd, doesn't matter. Then the rank is greatest integer of D by 2. If you directly start with SO2n plus 1, then the rank is n. For SO2n also rank is n. Okay.
Yeah.
So is this point clear, Debo?
Yeah.
I mean, this is physical way of argument. If you want more mathematical, so very good way to see this is, so you know the Lie algebra already, right? M, A, B, M, C, D. This is some delta, AC, M, B, D, and all those combinations.
Yeah.
Now you can simply just put in the values for which this side completely vanishes. So you will find that you have to take all of these to be different. So 1, 2, 3, 4. This is one possibility. And if you add a fifth one, it doesn't help. You can try this exercise.
Okay.
So literally, you know the D algebra, right, for SOD. So you just have to find those pairs there. So these
Okay.
pairs are nothing but rotations in that plane. That's why I physically argued what is happening.
I see.
Okay.
What
So
are you saying about the antisymmetric diagonal methods? That was not how do they
so my earlier point, if you remember my earlier point, I told you that a Lie algebra can be divided into diagonal and non-diagonal matrices. Diagonal are the Cartan elements and non-diagonal are the coset elements. Now look at SO2n plus 1 and SO2n. The Lie algebra is defined through a set of antisymmetric real matrices, which are for which you can never find a diagonal matrix, right? Because diagonal matrices are not antisymmetric, so they do not belong to this space. All of them are non-diagonal here. But that doesn't mean that non-diagonal matrices can also commute. Just the entries should be like that. You can try this exercise. Correct. So that was the point that I was mentioning, that here actually all of them are non-diagonal, but some of them still commute amongst themselves.
Okay.
So there is a distinction here also, like Cartan and coset, but it's not in the usual sense where you actually have diagonal matrices and non-diagonal matrices. Here all of them are non-diagonal. Still some of them commute, some of them don't.
Okay.
And the physical argument I gave was this picture: independent planes. These commute among themselves. And the generators will be very similar to those SO2. It will be like 0, 1, minus 1, 0. Just in that. So you have to draw a 4 by 4 matrix here for x1, x2, x3, x4. So if you remember SK's classes, then x1, x2, x3, x4. Here is also x1, x2, x3, x4. So if you are rotating between x1, x2, you will have this matrix and all of this will be 0. If you are rotating between x3 and x4, this will be 0. This will be 0, this will be 1, this will be minus 1, this all will be 0. Now you can see why these two matrices commute, x1, x2 and x3, x4. Now this I have stolen directly from this first example that I took. This 0, 1. Because that's like a rotation in a plane, right? Infinitesimal rotation in a plane. So you have to just generalize that to
extending it to 4 dimensions.
Exactly. So it's very easy to see that. And this is an anti-symmetric matrix, as you can see, but these commute amongst them. So because for one it appears here, for the other it appears here. Okay.
Yes. Yeah.
So as every mathematics book says, hard problems are always left for the reader, in this case audience. So the symplectic group is left in that sense, in the interest of time also. I just want to give a physical perspective now. So I have already talked about these things, W plus minus Z, photon, gluons and all these things. And I told you already that apart from these four infinite families of Lie algebras, you have five of them which do not fit in this classification, and these are the exceptional Lie algebras. And as I said, they have found their place in physics. So this is actually the last slide that I have, because this is part one and I don't want to put all the jargon here. So I'll divide this FDLA means finite dimensional Lie algebras. We divide it into classical and exceptional. So classical means this A and B and C and D N. All of these represent some kind of rotations, these classical Lie algebras. So for example, BN and DN series, which is the SO2N SO2N plus 1 and SO2N series, these are just rotations in real space, infinitesimal rotations in real space. AN, which is SUN plus 1, that is like a rotation in a complex space. So this is like RN, this is CN, so this is this stylized R that is written, this is CN, n-dimensional complex. And the symplectic group that you can show is the rotation in a quaternionic space. I will talk only for 2 minutes about what this quaternion and octonions are. And on the other side, you have exceptional Lie algebras. These are G2, F4, E6, E7. Very easy to see why this EFG. So you have exhausted A, B, C, D already. So after that comes EFG. So naturally, this Lie algebras are named in this series. This EFG is the exceptional series. And this subscript, this 2, 4, 6, 7, 8, this represents the rank of the Lie algebra. So G2 is a Lie algebra of rank 2, F4 is a Lie algebra of rank 4, E6, E7, E8 are Lie algebras of ranks 6, 7 and 8 respectively. And it is these E6, E7, E8 that have been found in supergravity, which is what I work on. And I will try to explain this in much detail in next talk. So before we stop, I'll just make a small comment on this last paragraph that is written here, this Hurwitz theorem. So you know real algebra, you know complex algebra, you know complex plane. So apart from real complex, there are two more number systems, you can say, or two more generalizations of this real and complex which are interesting. These are called division algebras, and these are quaternions and octonions. Okay, so I'll just show you what this is. So quaternion is just like it's a generalization of a complex number. So remember, complex number is A plus IB, where A, B are real numbers. Okay, a quaternion W is written as W1 plus IW2 plus JW3 plus KW4, where this I, J and K are imaginary units. They are just like I, but now these imaginary units have an algebra between them. I, J is K, J, K is I, and K, I is J. And each of them square to minus 1. Okay, so this is called a quaternionic space. So as you can see, it's a 4-dimensional space. I mean, a real 4-dimensional space, but these other 3 axes are imaginary now. So it's a generalization of complex number. And the claim is that you can think of the symplectic algebras as rotations, infinitesimal rotations in this space. Now, apart from this, there is another algebra, division algebra, which is interesting, and that is called the octonion algebra. And this is written as EIO. OI, where OI are real number. So here W1, W2, W3, W4 are all real numbers. Okay. And these EIs are the imaginary units. And they again have a multiplication table. Okay. The property of octonions is that they are not associative. That is, it matters how you multiply them. If you take OI, OJ, OK, and you multiply OJ, OK first and then multiply OI, that will not be equal to OI, OJ first and OK later. This is very different from quaternions or complex or real numbers, which are associative. Their multiplication is associative.
So is it about OIs or EIs that
OI,
is not
OI.
associated?
I mean, ultimately it is linked to EI because you can
EI.
expand. Sorry, this is actually abuse of notation. Thank you for pointing this out. So this
I
is
just got confused.
sorry. So let me call this a O1. Okay, and let's call this as E dot O. Okay, or let's call this A. This is better. So this O. So this is nothing but summation EI/OI. Okay. These OIs are real numbers and EIs are complex units. Okay. And if you take three of these octonian numbers, okay, they are not associative. Now is this clear?
Yeah.
Huh. But ultimately, as you said, it is actually related to this EI only, matlab this imaginary unit, because it's the multiplication of these imaginary units that is making the product of the numbers non-associative.
Can you also comment on this? Where are these schemes used? In what physical problems or systems? These quaternions and octonions.
So physics is not clear. So actually there is, if you read some old papers, there is an octonionic formulation of quantum mechanics, normal quantum mechanics, okay, which you read in, which you learn in MSc. So there are people have done some interesting things using that. I don't know how much physics it is, but from more physics perspective, I would say all of these exceptional Lie algebras are actually linked to octonian matrices. What does it mean? Take a matrix with octonian elements. Instead of real numbers or complex numbers, take the elements of the matrix to be octonian elements. Now look at the algebra of these matrices. You can find that it matches with one of these D2, F4, E6, E7, E8. Okay, and these algebras are important in condensed matter and also in high energy. So in that sense, you can connect it to physics. So in fact, I think there are experiments in condensed matter. Vishwas can tell you better. This E8, the excitations related to this E8 have been detected in experiment. So this is the physics. This octonian language is just a mathematical construct, but ultimately your goal is to understand these Lie algebras and the symmetries to solve
What does it offer as in, let's say, as a formalism? What uniqueness I might not be at that stage to understand personally, but let's say, for example, it gives a good conformal mapping or something like that. Like for example, in this complex scheme, like complex algebra, we have this property of getting all the solutions of an algebra. I mean, fundamental theorem of that algebra. I guess I don't know if I'm missing out. So we can cover all the solutions in complex plane, right? That gives us a bit fundamental thing.
I think there are two things here. What you are talking about is doing calculus with the division algebra. I am not even talking about doing calculus with this. This is just simple algebra with where I want to write some kind of a rotation matrix here. Okay, and with that I want to find these Lie algebras, these exceptional Lie algebras, which I have found in the condensed matter or supergravity systems, and then use this information of this Lie algebra. That is, if a theory has a symmetry, then what happens is if you find any observables, if you compute any observables in this theory, that is, if you measure something, that measurement should not be affected by the symmetry transformation, right? Because that is what symmetry means. Correct. So this is actually used to find the observables. You use the symmetry transformations to compute the observables,
Mm-hmm. Okay.
which can be correlation functions or scattering amplitudes, whatever.
Mm-hmm.
Okay.
Yeah.
So this is the Hurwitz theorem. You can look it up in the book that I posted on the group. These Lie groups and Lie algebras. It's given nicely there. There are exactly 4 division algebras with composition property: real, complex, quaternion, and octanion. And with this, I will end the talk. So if you have any questions, you can ask. The talk for today is over.